In absolute darkness, 13 billion years ago, something impossible is glowing. 300 million years after the universe began, giant spheres of hydrogen shine. They illuminate the infant cosmos with a strange, impossible light. But these immense objects should not exist yet. They are not stars as we know them today. They burn without the fire of nuclear fusion. Something invisible powers them from within. This unseen substance is tearing itself apart inside. NASA's James Webb Space Telescope has finally found them. These discoveries completely rewrite our cosmic history. The first dark stars are waiting in the ancient void. The James Webb Space Telescope aimed its golden mirrors. It pointed toward a patch of seemingly empty sky. It found something there that should not exist. Scientists on Earth expected to see only darkness. They instead found light blazing from an ancient time. The light came from when the universe was barely 300 million years old. Nothing should have been bright enough to see then, not across such a vast and incomprehensible cosmic distance. These strange objects glowed with an impossible intensity. They appeared as tiny, faint red dots in the images. They were scattered across the ancient infant heavens. Every astronomer knows the accepted cosmic timeline. First, there is a long period of absolute darkness. Then vast hydrogen clouds collapse under their own gravity. Nuclear fusion reactions ignite deep in their cores. The first generation of true stars is finally born. But these glowing objects exist before that process could happen. They shine from an epoch when the universe was still cooling. It was still organizing itself out of chaos. It was still figuring out how to make the first generation of anything. The powerful telescope captured their faint, ancient light. That light had traveled for over 13 billion years. It crossed an ever-expanding universe to reach our detectors. Catherine Fries, a physicist, studied the new images. She looked at them with a feeling of growing excitement. She had predicted the existence of these objects. Her prediction came back in 2007. She had called them dark stars in her theory. For years, her revolutionary theory waited for new technology. It needed a telescope capable of seeing that far back in time. Now the evidence was finally appearing in the data streams. It came from the most powerful space observatory ever built. What she found in the data matched her calculations. The match was almost perfect in every single detail. The objects appear incredibly red because of cosmic expansion. As the fabric of space itself stretches over time, the light traveling through it also stretches. It shifts toward longer and therefore redder wavelengths. The more distant a cosmic object is, the redder it appears. These faint dots rank among the reddest objects ever detected. This places them in the universe's extreme infancy. But their incredible brightness defies all conventional explanation. It cannot be explained using standard stellar physics. Fusion-powered stars simply cannot form this early. The process requires very specific physical conditions. Those necessary conditions did not exist yet in the universe. Heavy elements had not yet been created by stars. Efficient cooling mechanisms that allow gas clouds to collapse were absent. The entire cosmic environment was far too hot. It was too chaotic and too pristine for normal star formation. Something else must be generating all of this powerful light, something that is using a completely different power source. The telescope's spectroscopy instruments measured the light. They measured the different wavelengths coming from these objects. One specific target showed an unusual absorption feature. This dark line appeared at 1,640 angstroms. This unique signature does not appear in normal galaxies. It suggests something exotic is happening there, something that has never been observed before in cosmic history. The strange pattern matches the theoretical predictions. It matches predictions for objects powered by dark matter, not objects powered by normal nuclear reactions. 4 strong candidates emerged from the initial survey data. Each one of them existed in a very narrow time window. Between 300 and 600 million years after the Big Bang, each one displayed characteristics inconsistent with being a small galaxy. They did not look like they were filled with regular stars. Their temperatures were completely wrong for normal stars. Their calculated sizes were also completely wrong. Their chemical spectra were completely wrong as well. Everything about them pointed toward a new class of celestial object, a class that cosmologists had theorized but had never confirmed. The stunning discovery sent ripples through the astronomical community. If these objects are truly dark stars, they solve multiple mysteries. They solve mysteries that have been plaguing our understanding of cosmic evolution. They help to explain how supermassive black holes formed so quickly. They also explain why early galaxies appear much brighter than predicted. They might even finally reveal the nature of dark matter itself. But what exactly makes a dark star shine so brightly? The answer lies in something completely invisible to our eyes. It is consuming itself deep inside massive hydrogen clouds. Picture a vast cloud of hydrogen and helium gas. It is floating in the darkness of the early universe. It stretches across distances that would take light weeks to cross. Inside this enormous primordial cloud, something strange is happening. Invisible particles are colliding with incredible violence. They are tearing each other apart in countless numbers. This process releases massive amounts of pure energy. This is not the process of nuclear fusion. This is a process called annihilation. Dark stars are theoretical objects proposed decades ago. The concept behind them is straightforward but revolutionary. What if the first luminous objects were not powered by hydrogen, not by hydrogen smashing together to make helium? What if they were powered by dark matter destroying itself? The energy released could heat a gas cloud from within. It could make the entire cloud glow brightly. It would glow without ever compressing into a dense stellar core. These objects would look nothing like the stars we see today. A normal star like our Sun has a nuclear furnace. This furnace is at its very center a tiny hot core. It is surrounded by layers of progressively cooler gas. All of the energy comes from that incredibly hot core. Dark stars work in a completely different way. Their energy source is distributed throughout their entire volume. It exists wherever dark matter particles happen to meet. Wherever they meet, they annihilate and release their energy. Think of a regular star as being like a bonfire. All of its heat is concentrated in one single spot. A dark star is more like a dense fog lit from within. It glows evenly throughout its enormous structure. This fundamental difference means dark stars can grow to immense sizes that would be completely impossible for fusion-powered objects. Without a concentrated core fighting against gravitational collapse, they can swell to truly monstrous and unbelievable proportions. Confirmed observations from the James Webb Space Telescope show objects that match these predictions with remarkable accuracy. They are puffy, diffuse, and incredibly luminous. Their temperatures suggest they are not compressed enough for fusion. Their chemical signatures show only hydrogen and helium. These are the primordial elements created in the Big Bang. Everything about them screams that they are different. They are different when compared to any star we have ever studied. The theory requires 3 specific conditions to work. First, you need a region of space with high dark matter density. Second, that dark matter must be capable of self-annihilation. Third, the resulting energy must get trapped inside the hydrogen cloud. It cannot be allowed to radiate away freely into space. In the early universe, all 3 conditions existed. They existed simultaneously in special locations. These locations are known as dark matter halos. Cosmin Illier is an astrophysicist who has studied these objects. He has spent years refining the mathematical models. His detailed calculations show that dark stars could reach incredible masses that are equivalent to 1 million suns. They could shine with the brightness of 10 billion suns. These numbers sound absurd and almost unbelievable, but they emerge naturally from the physics of dark matter. They emerge from the unique environment of the infant cosmos. The breakthrough came when spectroscopic data from the telescope arrived. It revealed exact matches to the predicted signatures. The specific wavelengths of light were a perfect match. The ratios of the different elements were also a match. The overall luminosity of the objects lined up as well. After many years of waiting, the theory had observational support, but finding these potential dark stars raises more questions. It raises more questions than it actually answers. How exactly does dark matter annihilate itself? What type of fundamental particle is destroying itself? What is happening inside these giant cosmic objects? The answers might finally reveal a deep cosmic secret. They could tell us what makes up 1/4 of everything in existence. Dark matter does not emit any form of light. It does not absorb any form of light either. It does not interact with the electromagnetic forces at all. For decades, scientists have detected it only through gravity. They watched how galaxies spin much too fast for their visible mass. They saw how clusters of galaxies hold together too strongly. Something invisible is out there in the cosmos, and it outweighs all the stars and gas we can see. It outweighs them by a factor of 5 to 1. The leading candidate for dark matter is a type of particle. It is called a WIMP, which is a simple acronym. It stands for a weakly interacting massive particle. These hypothetical objects would have a specific mass, somewhere between 10 and several hundred times heavier than a proton. They would pass through normal matter almost without any interaction. This is why we have never been able to catch one, despite building increasingly sensitive detectors deep underground. But WIMPs have one crucial and important property. They might be their own antiparticles in the universe. When a particle meets its corresponding antiparticle, both of the objects vanish in a bright burst of energy. Their mass converts directly into other forms of energy. According to Einstein's famous equation E equals mc², two particles go in and pure energy comes out. This incredible process is known as annihilation. It is one of the most efficient power sources imaginable. In normal conditions throughout the universe today, dark matter particles are spread much too thinly. They cannot annihilate with any significant frequency. They drift silently through the vastness of space. They occasionally pass near each other but rarely collide. The annihilation rate today is almost completely negligible. But in the early universe, the conditions were vastly different. All matter was compressed into much smaller volumes. Dark matter halos formed as the first cosmic structures. They were the first things to condense out of the cosmic soup. They created regions where dark matter density was millions of times higher. Inside these early halos, dark matter particles would collide constantly. Every single collision between two WIMPs would release energy. It would release a cascade of pure, raw energy. That energy does not simply vanish into nothingness. It transforms into photons, electron-positron pairs and neutrinos. The neutrinos escape from the cloud almost immediately. They escape because they interact with almost nothing at all. But the photons and the electrons get trapped inside. They bounce around inside the dense hydrogen cloud. They transfer all of their energy to the surrounding gas. This heating mechanism is very subtle but also very powerful. Each annihilation event deposits a huge amount of energy. It is equivalent to the entire rest mass of both particles. For a 100 giga-electron-volt WIMP, that is a lot of energy. That is roughly 100 times the mass energy of a proton. It is converted to heat with every single collision. Multiply this by trillions upon trillions of annihilations. These are happening every second throughout the entire cloud, and you generate enough power to make a star-sized object shine. The entire process is remarkably self-regulating. As the giant cloud heats up, its internal pressure increases. This pressure counteracts the inward pull of gravitational collapse. The object reaches a stable state of equilibrium. Gravity pulling inward exactly balances the pressure pushing outward. Unlike fusion stars, which require extreme densities to ignite, dark stars can maintain this balance while remaining diffuse. They never compress enough to start hydrogen burning. They do not need to because they have another power source. Confirmed mathematical models show this mechanism works. It works for a very specific range of dark matter properties. The annihilation cross-section must be strong enough. It must be strong enough to generate sufficient heat, but it must also be weak enough that dark matter particles survive. They must survive in large numbers to the present day. The particle's mass must fall within a certain window. The conditions must exist in regions where hydrogen is abundant, but it must not yet be organized into normal stars. All of these specific requirements aligned perfectly. They aligned in dark matter halos during the first few 100 million years. The big question is whether nature actually exploited this opportunity. The immense scale of dark stars defies our human intuition. Imagine an object that is so large and diffuse. Light would take several weeks to cross from one side to the other. Picture a gigantic ball of glowing hydrogen gas. It could easily swallow thousands of entire solar systems. These are not stars as we currently know them. They are true cosmic monsters that dwarf our own sunday. Our sun would look like a tiny grain of sand next to them. A typical dark star could reach 1 million times the mass of the sun. It could shine 10 billion times brighter than our sunday. To put that incredible luminosity into some perspective, our entire Milky Way galaxy contains roughly 400 billion stars. Their combined light output is just 40 billion solar luminosities. A single large dark star could match a meaningful fraction of that. It could match the brightness of an entire galaxy. When you compress that much light into what is essentially a point source when viewed from cosmic distances, it creates the impossibly bright dots that confused astronomers. The structure of these objects is completely unlike anything we see today. Normal massive stars pack all of their mass into a compact sphere. A star that is 10 times the Sun's mass might be 10 times wider. Even the largest known stars today are only about 1,500 times wider. They are only 1,500 times the Sun's diameter. Dark stars would dwarf them completely in sheer size. They could potentially reach 10 times the width of Earth's orbit. This enormous size comes directly from the distributed heating mechanism. Fusion stars must compress until their cores reach millions of degrees. This is enough to overcome the repulsion between hydrogen nuclei. That compression creates enormous densities at the very center. The outer layers of the star remain relatively thin. Dark stars never undergo this extreme form of compression. The heat from the dark matter annihilation is spread throughout the volume, so the entire structure can remain puffy and very diffuse. It can still maintain enough pressure to resist gravity. Theoretical calculations show these objects could survive for millions of years. They could possibly survive for even longer than that. They would need to capture fresh dark matter from their surroundings. Unlike fusion stars, which burn through their fuel predictably, dark stars will last as long as their dark matter supply holds out. In the dense halos where they form, that supply could be unlimited. Dark matter would keep falling inward toward the star. It would be captured by the star's immense gravity. It would then add to the overall fuel reservoir. The brightness of a dark star varies depending on certain properties. The mass and properties of the dark matter particle are key. For 100 giga-electron-volt WIMPs, a 1 million solar mass dark star would shine. It would shine with exactly the intensity needed to match the observations. For lighter particles, the stars might be somewhat dimmer, but they would still be extraordinarily bright by any cosmic standard. The range of possible configurations all fall within the window, a window that early universe observations are now revealing. But here is what makes this discovery truly staggering. These giants are not the strangest things that the telescope found. The telescope detected something else in the early universe. Something that initially looked like tiny, distant galaxies, but it might be something that is far more exotic. Astronomers now call them little red dots, and they are rewriting our understanding of cosmic evolution. They are rewriting it in ways that even dark stars cannot explain. What appears at first to be simple is turning out to be a puzzle, the most complex puzzle in all of modern cosmology. Dale Kosevsky was analyzing the new telescope data. He noticed that something was wrong with the numbers. Small, intensely red objects were appearing in the images. They were appearing throughout the deepest images ever taken. They existed in an era when the universe was less than 1.5 billion years old. At first, his team assumed that these were compact galaxies. They thought they were dense collections of stars packed into tiny regions. Then they took a much closer look at the data. The spectra that they measured were truly bizarre. Gas was moving at nearly 1,000 kilometers per second. It was moving at these speeds around the objects. These speeds indicate something with tremendous gravity at the center. Normal galaxies do not show this kind of behavior. Small galaxies especially should not have material moving so fast. The motion suggested the presence of accretion disks. These are the swirling funnels of matter that form around black holes. They form when material spirals into a black hole. But if these were black holes, they were far too massive. They were too massive for their small host galaxies. The telescope found over 700 objects that might date from this era. The little red dots emerged as a distinct population. They appeared around 600 million years post-creation. They underwent a rapid decline about 1.5 billion years later. Their appearance and disappearance seem to trace a fundamental transition. A transition in how the universe organized itself. About 70% of the targets showed evidence for black holes. Supermassive black holes were at their centers. These were not the small black holes created by dying stars. These were monsters that weighed millions of solar masses. They existed when the universe had barely had time to form anything. Traditional black hole formation theories cannot account for them. Stars need time to form, live, die, and leave behind remnants. Those remnants then need time to merge and grow larger. The timeline for this to happen is simply too short. Unless dark stars provide the necessary seed for them, when a dark star finally exhausts its dark matter fuel, the supporting pressure inside it completely disappears. The entire million solar mass cloud of gas collapses inward. It collapses with absolutely nothing to stop its fall. No fusion has occurred, so there is no outward radiation pressure. The collapse is catastrophic, total, and irreversible. Within a cosmologically brief moment, the entire structure plunges. It plunges past the point of no return. It forms a black hole in a direct collapse event. This black hole starts with a mass already in the millions. It is already in the millions of solar masses range. It does not need to grow from a tiny stellar mass seed. It does not need to overcome the Eddington limit. This is the theoretical maximum rate at which black holes can consume matter. It begins its life large and can immediately start accreting. It can accrete material from its surroundings without waiting. It does not have to spend eons working its way up from stellar mass. The timing of this process works out perfectly. Dark stars form in the first few 100 million years. They shine for perhaps 1 million years, maybe longer. Then they collapse into black holes right when the telescope sees them. The telescope starts detecting impossibly massive black holes. The correlation between the two is too strong to ignore. But some of the little red dots appear in regions that look nearly empty. They sit in cosmic voids where there should not be enough matter. Not enough matter to feed a growing supermassive black hole. Their strange isolation contradicts everything we thought we knew. We thought we knew how massive black holes form and grow. Anna Christina Eilers called this discovery perplexing. These quasars are not necessarily in the highest density regions. Some of them seem to be in the middle of nowhere. How do you grow a monster in an empty cosmic desert? 25% of the universe is made of something we cannot see. We cannot touch it, and we cannot detect it with any instrument, not with any instrument that measures any form of light. We simply call this mysterious substance dark matter. And it is not dark in the sense of being shadowed. It is dark because it does not interact with electromagnetic radiation. No wavelength of light can bounce off of it. No telescope can ever capture its image directly. We know that it exists only because galaxies spin wrong. In the 1970s, an astronomer named Vera Rubin measured galaxy speeds. She measured how fast stars orbit in spiral galaxies. The pattern that she found made no sense at all. Stars that were far from the galactic center were moving just as fast. They were moving as fast as stars near the center. They should have been moving much more slowly, according to Newton's laws. Something invisible was pulling on them with its gravity, something that outweighed all of the visible stars and gas combined. Clusters of galaxies showed the exact same problem. The gravity that was needed to hold them together was 5 times stronger. It was stronger than what all of their visible matter could provide. For decades, physicists have proposed various candidates for this missing mass. Maybe it was a population of ancient black holes. Maybe it was a population of dead stars that were too dim to see. Maybe it was some kind of exotic particle left over from the Big Bang. Observations have gradually ruled out most of the conventional explanations. Whatever dark matter is, it must be a new type of particle, a particle that is not included in our standard model of physics. The leading candidate for this particle is the WIMP. These particles would have a mass between 10 and several hundred times a proton. This places them in a sweet spot for explaining dark matter's abundance. The name comes from how they are thought to interact. They interact weakly through forces similar to the weak nuclear force. This is the force that governs certain types of radioactive decay. This is much, much weaker than the electromagnetic force. This is why WIMPs can pass through normal matter almost without any effect. The elegance of the WIMP theory lies in a strange coincidence. Cosmologists call this coincidence the WIMP miracle. When you calculate how many particles with this interaction strength should survive, how many should have survived from the early universe, you get almost exactly the dark matter density we observe today. This is not a result of any fine-tuning of the parameters. It emerges naturally from the basic physics of the early universe. The annihilation rate, the expansion rate, and the final density all connect. They connect through equations that give the right answer without adjustment. Here is how this process worked in the early universe. Initially, all particles were in a state of thermal equilibrium. They were constantly forming and annihilating in the hot cosmic soup. As the universe expanded and cooled, the temperature dropped. It dropped below the threshold needed to create new WIMP pairs. Existing WIMPs continued to annihilate each other when they collided. This caused their total numbers to decrease exponentially, but the expansion was also reducing the overall density. This made collisions between the particles much rarer over time. At some critical moment, the universe expanded fast enough. WIMPs could no longer find each other to annihilate. The process of annihilation then effectively froze out. It left a relic population of WIMPs that has been drifting ever since. The number density of these particles got locked in at that moment. It has simply been diluted by the expansion of space from then until now. If you calculate this freeze-out density using weak force interaction strengths, you get the dark matter abundance that gravitational measurements require. But confirming the WIMP theory requires detecting these particles. We must detect them directly or find indirect evidence of their annihilation. Despite decades of increasingly sensitive experiments, no one has caught a WIMP. Until now, perhaps, with the discovery of dark stars. The dark stars might be showing us WIMP annihilation in action. Those trillions of collisions happening every second inside the early clouds. They are creating exactly the signatures that we are now seeing. When two WIMP particles collide, they do not just bounce off each other. They do not act like billiard balls in a simple collision. They completely vanish from existence in a flash of energy. Both of the particles cease to exist in that moment. Their entire rest mass energy is converted into other particles. According to the rules of quantum field theory, the universe is a strict accountant. Energy can never be created or destroyed in any process. It can only be transformed from one form to another. In this case, mass is transformed into a cascade of lighter particles. These particles carry away all of the initial energy. The exact products of the annihilation depend on the specific channel, but typical outcomes include photons, electron-positron pairs, and neutrinos. Neutrinos barely interact with anything at all in the universe, so they escape from the collapsing gas cloud immediately. They carry all of their energy away into the vastness of the void. This energy is effectively lost to the forming star, but the photons and the charged particles like electrons get trapped. Picture a photon trying to escape from deep inside a dense hydrogen cloud. It travels only a tiny distance before it hits a hydrogen atom. It gets absorbed, and then it is re-emitted in a random direction. The photon takes what physicists call a random walk. It zigzags through the dense gas in a drunken path. This path might point inward just as often as it points outward. The denser the gas, the shorter the distance between these collisions, and the longer it takes for the energy to work its way out. In the conditions of early dark star formation, the gas is very dense. It is dense enough that photons and electrons deposit all their energy. They deposit it into the surrounding hydrogen before they can escape. The hydrogen atoms in the cloud absorb all of this energy. They then start moving much faster as a result. Temperature is just the average speed of the particles in a gas. So faster moving atoms mean that the temperature is higher. The energy that was once locked in dark matter's mass is now heat. It is now heat that is distributed throughout the gas cloud. This heating has a crucial and important effect on the cloud. It creates a great deal of internal pressure. Hot gas pushes outward with a force that is proportional to its temperature. As dark matter continues annihilating and dumping energy into the cloud, the temperature of the cloud continues to rise. The pressure inside the cloud continues to increase as well. Eventually, the outward pressure force becomes strong enough. It becomes strong enough to counteract the inward pull of gravity. The cloud then stops collapsing and reaches a stable equilibrium. Calculations show that for 100 giga-electron-volt WIMPs with standard cross-sections, this balance occurs at densities that are far lower than fusion requires. The cloud never compresses enough to ignite hydrogen burning. Instead, it settles into a puffy, extended structure. It is held up entirely by the energy from dark matter annihilation. A dark star has finally been born in the infant universe. The power output of these objects is truly staggering. Each annihilation event converts mass to energy with 100% efficiency. This is in contrast to fusion, which is much less efficient. Fusion converts less than 1% of mass to energy. The amount of energy released per unit of mass is 100 times greater. Given the high dark matter densities in the early universe halos and the continuous replenishment of dark matter falling into the star, the total luminosity can reach billions of solar luminosities. The process is self-sustaining as long as dark matter keeps flowing in. The star captures more dark matter from its surroundings. It does so through its powerful gravitational pull. That captured dark matter then sinks toward the center. This is where the densities are the absolute highest. The annihilation rate depends on the density squared. So the central regions of the star produce the most power. But unlike fusion stars, the energy generation is spread out. It is spread throughout the entire volume of the star. It is not concentrated in a tiny dense core. This distributed heating is what allows dark stars to grow so large. They do not have the structural constraint of needing a thermonuclear explosion. They do not need to contain this explosion at their center. They are more like giant cosmic light bulbs powered from within. They glow steadily without the dramatic dynamics of fusion-powered objects. But this raises a critical question for astronomers. Why could not normal fusion stars have formed? First, normal star formation follows a well-understood sequence of events. A large cloud of gas begins to collapse under its own gravity. As this cloud contracts, gravitational potential energy is converted to heat. The center of the cloud gets hotter and denser over time. The outer layers of the cloud continue to fall inward. Eventually, the core of the cloud reaches a critical temperature. The temperature is around 10 million degrees Celsius. This is hot enough for hydrogen nuclei to overcome their repulsion. They can then fuse together to form new helium nuclei. This fusion reaction releases a tremendous amount of energy. This energy creates an outward pressure that halts the collapse. A new stable star has finally been born into the universe. This entire process requires some very specific ingredients that did not exist in the very early universe. The most critical missing component was efficient cooling. For a gas cloud to be able to collapse into a star, it must be able to radiate away a great deal of its energy. If the energy cannot escape, the pressure inside builds up. This pressure prevents any further contraction of the cloud. In the modern universe, atoms and molecules provide numerous ways to cool. Collisions between particles can excite electrons to higher energy levels. When those electrons drop back down, they emit photons. These photons then carry the excess energy away from the cloud. But in the pristine gas emerging from the Big Bang, cooling was limited. The universe contained only hydrogen and helium at that time. It also contained just trace amounts of the element lithium. There was no carbon, no oxygen, no nitrogen, and no other metals. The word metals in astronomy means any element heavier than helium. The early universe was completely metal-free by its very definition. These heavy elements had not yet been created in the cosmos. They can only form inside of stars through the process of nuclear fusion. Hydrogen gas can cool through the formation of molecular hydrogen. Two hydrogen atoms can bond together to form a simple molecule. These molecules can then radiate energy away through their transitions, but forming molecular hydrogen requires specific conditions. The process also proceeds very slowly over time. The cooling rate is not efficient enough to allow for rapid collapse. It cannot lead to the formation of dense, stellar cores. In most circumstances, without this efficient cooling, gas clouds in the early universe would just heat up as they contracted. They would generate enough pressure to resist any further collapse. The structures that formed would be larger and more diffuse than modern stars. They would be protostellar objects that never reached the right densities. They would never ignite the process of nuclear fusion. Some clouds did eventually cool enough to form the first true stars. Astronomers call these population 3 stars, the first generation. But this entire process took a great deal of time to happen. Dark stars are able to bypass this entire problem completely. They do not need to compress to extreme densities. They do not need any efficient cooling mechanisms to form. The energy from the dark matter annihilation provides the support. It provides the necessary pressure support at relatively low densities. The heating of the gas happens from within the cloud. It does not happen from gravitational compression alone. So the cooling rate of the gas becomes much less important. Dark stars can form in conditions where fusion stars simply cannot. The timeline of these events matters enormously to the overall story. The James Webb Space Telescope is detecting bright objects at redshift 14. This corresponds to just 300 million years after the Big Bang. This is an extraordinarily early time in cosmic history. Traditional stellar evolution models suggested that we should not see much. Not much light should be coming from this early era. Not enough time had passed for efficient star formation to begin. The discovery of these bright early objects created a crisis. Some scientists called it a universe-breaking crisis. If all of that early light came from normal fusion stars, it would require impossibly rapid and efficient star formation. The mass would need to be turned into stars at very high rates, rates that are higher than any observed mechanism can explain. Something about our models of the early universe would be wrong, but if much of that light comes from these new dark stars, the entire problem simply vanishes into thin air. Dark stars can form very quickly and shine incredibly intensely. They can explain the observations without breaking the laws of physics. The evidence for them keeps pointing in one single direction. These early luminous objects are not behaving like normal star clusters. They are behaving like something that we have never seen before. Before galaxies existed and before any stars ignited, before any planets had formed, the universe was organizing itself. It was organizing itself on a scaffold made of dark matter. In the first moments after the Big Bang, there were tiny fluctuations. Quantum fluctuations in density were stretched to cosmic scales. This happened during a period called cosmic inflation. These ripples in the distribution of matter and energy seeded all future structure. Dark matter was the first substance to respond to them. Unlike ordinary matter, dark matter did not interact with the radiation field. It did not interact in a way that would smooth out structures. Regular matter was tightly coupled to photons in the early universe. This was due to the powerful electromagnetic forces. Any attempt by normal matter to clump together would be resisted. The radiation pressure would be pushing outward against it. Dark matter had no such constraint acting upon it. It only felt the force of gravity, both its own and that of space-time. The overdense regions in the universe began to collapse. This happened where the dark matter density was slightly higher. Gravitational attraction then pulled in more dark matter. It pulled it in from all of the surrounding regions. These regions grew denser, which increased their gravitational pull. This then accelerated the infall of more material. This created a runaway process of structure formation. Within a few 100 million years, the first dark matter halos had condensed. A halo is not an object that you can see or photograph. It is a region of space where dark matter has accumulated. It has accumulated to densities far above the cosmic average. Think of it as an invisible bowl carved into space-time. It is carved by the force of gravity itself. Dark matter particles are orbiting and swarming throughout its volume. The densest part of the halo sits at the very center. The density falls off gradually toward the outer edges. It follows what astronomers call a specific density profile. Simulations have shown that these first halos were quite small. They were small by the standards of modern galaxies. Perhaps only 10,000 to 1 million times the Sun's mass. This was their total dark matter content in the beginning, but relative to their small size, they were incredibly dense. Dark matter particles were packed together millions of times more tightly than they are in the universe at large today. This high density created the ideal conditions for annihilation. Regular matter, which was still coupled to radiation, could not yet collapse. It could not fall into these dark matter halos at first. But as the universe continued expanding and cooling, a change occurred. The temperature dropped below 3,000 degrees Kelvin. At that point, electrons and protons combined to form neutral hydrogen. This crucial event in cosmic history is called recombination. With neutral atoms came the decoupling from the radiation field. Matter and light finally went their separate ways. Now hydrogen and helium gas could fall into the dark matter halos. Gravity pulled the gas inward toward the deepest potential wells. As the gas fell, it picked up speed and began to heat up. It heated up from the process of gravitational compression. The gas settled into the central regions of the halos. It formed dense clouds that would become the first protostellar objects. But before nuclear fusion could ignite in these clouds, dark matter annihilation started heating them from within. The halo environment was absolutely perfect for dark star formation. You had a high density of dark matter providing abundant fuel. You had pristine hydrogen and helium gas providing the visible material. You had gravitational wells that were deep enough to trap the annihilation products. All three of the necessary conditions existed simultaneously. They existed in a way that would never be repeated in cosmic history. This happened once heavy elements began to pollute the gas. These elements would alter the cooling properties of the gas forever. These mini halos, as cosmologists call them, were the wombs of cosmic dawn. Inside of them, the universe experimented with its first luminous structures. Some of these halos might have formed dark stars. Others might have formed the first fusion stars through different mechanisms. Many of them probably did nothing interesting at all. They simply merged with larger structures at a later time. But the halos that did create dark stars left behind signatures that we are only now beginning to be able to detect. The densest concentrations of these halos produced the most spectacular results. One particular object has captured intense scientific attention. Among the 4 dark star candidates identified in the initial survey, one of them stands out from all of the others. Scientists have labeled it with a technical designation. This designation encodes its position on the sky and its discovery survey. But what matters is not its name, but a single line, a single dark line in its spectrum of light. This is an absorption feature at 1,640 angstroms. It should not be there if this were a normal galaxy. Spectroscopy is the most powerful tool in all of astronomy. By spreading light into its component wavelengths, you can determine what atoms and molecules exist in distant objects. You can determine how hot they are and how fast they are moving. You can also determine what processes are generating their light. Every single element leaves behind a unique fingerprint in the light, a specific pattern of lines where light gets absorbed or emitted. By reading these unique fingerprints in the spectrum, astronomers can decode the composition and behavior of cosmic objects that are billions of light years away from us. When Cosmin Illier examined this particular candidate spectrum, he immediately recognized the significance of what he was seeing. The absorption feature matched the predictions for supermassive dark stars. It matched them almost exactly in every single detail. Normal galaxies do not show this specific pattern in their spectra. The wavelength corresponds to helium transitions that occur under specific conditions. Very specific temperature and density conditions are required. These conditions match the outer layers of a dark star, but they do not match the stellar populations of early galaxies. This is what scientists refer to as a smoking gun. It is a piece of evidence that is so specific and unusual. It points to only one possible explanation for the phenomenon. In this case, the explanation is that we are looking at an object that is powered by dark matter annihilation, not an object that is powered by nuclear fusion. The theory had predicted this signature years before the telescope launched. Now, observation has confirmed that it exists in at least one target, a target from the very early history of the universe. Additional observations were made using the Atacama Large Millimeter Array. This is a ground-based radio telescope located in Chile. It detected the presence of oxygen in the vicinity of this object. Oxygen is a heavy element that is created only inside of stars. It is created through the process of nuclear fusion. Its presence means that either some fusion stars have formed nearby, or this dark star exists in a region where a regular galaxy has already formed, a galaxy that has polluted the gas with a significant amount of metals. Either way, the environment around the object is more complex. It is more complex than a simple isolated dark star. One possibility is that the dark matter halo merged with a small galaxy. This would combine dark star formation with conventional stellar populations. Another possibility is that dark stars and fusion stars formed at the same time. They could have formed in the very same dark matter halo. Dark matter annihilation could be heating some of the gas clouds, while molecular hydrogen cooling allowed others to collapse into fusion objects. The early universe was a very chaotic and dynamic place. Different formation mechanisms were competing with each other, and sometimes they were cooperating with each other as well. But the presence of metals does not invalidate the dark star interpretation. It actually strengthens the case for this interpretation. It shows that the environment is consistent with early galaxy formation scenarios. Scenarios where multiple processes occurred in close proximity. The key point is that the spectral signature remains unexplained. It is unexplained by conventional stellar physics alone, and it matches the predictions of dark star theory remarkably well. This single object has now become the focal point of intense study. Every available instrument is being pointed at it. Astronomers are trying to gather additional data on it. The team is working to automate the search process. They are using machine learning algorithms to scan through the data. These algorithms can scan through thousands of telescope spectra. They are looking for similar patterns in the light. This is a task that would take human analysts years to find manually. If dark stars were a common phenomenon in the early universe, more candidates for them should exist in the archived data. Finding a dozen or more of these objects would transform the field. It would transform this from an intriguing possibility into an established fact. The implications of this extend far beyond just confirming a prediction. If we have found dark stars, we have found direct evidence. Direct evidence of dark matter annihilation in action. We have opened a new window into the nature of the mysterious particles, the particles that dominate the universe's total mass budget. We might finally be seeing the invisible made visible. It is made visible through its effects on the first luminous structures. The universe begins as a point of infinite density. It has infinite temperature and is expanding outward. This violent explosion creates space and time itself. In the first fractions of a second, fundamental forces separate. Particles and antiparticles appear and annihilate in a roiling plasma. The temperatures exceed trillions of degrees Celsius. This is known as the Planck era in cosmology. It is a time when quantum mechanics and gravity merge. They merge in ways that we still do not fully understand. As the expansion of the universe continues, it cools rapidly. Within just a few microseconds, quarks bind together. They form the first protons and neutrons in the universe. Within a few minutes, the process of nuclear fusion begins. It creates helium from hydrogen in the primordial soup. By the time the universe is about 20 minutes old, the abundance of the light elements has been set. Roughly 75% of the matter is hydrogen, 25% of the matter is helium. There are also trace amounts of the element lithium. This specific ratio will persist for a very long time. It will persist until stars begin forging heavier elements. This will happen billions of years later in cosmic history. For the next 380,000 years, matter and radiation remain coupled together in an opaque fog. Photons cannot travel very far before they scatter off free electrons. The universe is essentially a giant glowing cloud. It is bright everywhere, but it is transparent nowhere. Then the process of recombination finally occurs. Electrons and nuclei combine to form neutral atoms, and suddenly light can travel freely through space. The cosmic microwave background radiation was emitted at this moment. This is the light that we can still detect today. Now the cosmic dark age finally begins in the universe. No stars exist yet, and no galaxies have formed. The universe contains only neutral gas and dark matter. They are slowly organizing themselves under the pull of gravity. This era lasts for approximately 100 million years. It is a period when the cosmos is truly and utterly dark. It is lit only by the fading afterglow of the Big Bang. At 300 million years we reach the epoch when the James Webb Space Telescope is detecting its brightest objects. This is still an incredibly early time in cosmic history. The universe is only 2% of its current age. For comparison, if the cosmos today were a 50-year-old person, we are looking at events from their very first year of life. The structures that are forming now are the seeds of everything. They are the seeds of everything that will come later. Temperatures have dropped to just a few dozen degrees above absolute zero. This is true in most regions of the universe at this time. Though collapsing gas clouds are heating up from compression, the expansion rate of the universe is still very high. This means that structures must form very quickly. They must do so to avoid being diluted into irrelevance. Dark matter halos have already condensed in the overdense regions. They are creating gravitational wells that are trapping gas. The hydrogen and helium gas is being pulled into them. The environment at this time is very harsh and chaotic. When two dark matter halos collide and merge, shock waves are created that heat the gas to millions of degrees. When gas falls into the halos, it releases gravitational energy. This can power intense bursts of radiation. The first generation of stars is beginning to light up the darkness. They could be dark stars or fusion stars or both. Their powerful ultraviolet light starts to reionize the neutral hydrogen. It creates bubbles of ionized gas that grow and overlap. This era is called the cosmic dawn by astronomers. It represents one of the most important transitions in universal history. Before the cosmic dawn, the universe was cold, dark, and structureless. After the cosmic dawn, galaxies began forming in large numbers. Stars began creating the first heavy elements, and the stage was finally set for planets and eventually for life. We are witnessing the very birth of complexity from simplicity. The objects that the telescope sees from this epoch are not minor curiosities. They are the pioneers of the luminous universe. They are the first structures to achieve brightness in a dark cosmos. Understanding how they formed and what powered them is essential. It is essential to understanding how we got from the Big Bang, how we got to the rich, structured universe we inhabit today. And the evidence increasingly suggests that dark matter played a direct role. It played a direct role in the process of cosmic dawn, inside a collapsing gas cloud in the early universe. A specific set of numbers determines what happens next. Temperature measures the average energy of all of the particles. Density counts how many particles occupy each cubic centimeter of space. Together, these two quantities control the fate of the cloud. They determine whether it forms a dark star, a fusion star, or nothing. The boundaries between these different outcomes are sharper than you might expect. For the process of nuclear fusion to ignite in a star's core, the core of a collapsing cloud must reach a certain temperature. It must reach approximately 10 million degrees Celsius. At any lower temperatures, the protons in the gas lack sufficient energy. They cannot overcome their mutual electromagnetic repulsion and merge. Below this critical temperature threshold, nothing will happen. No matter how long you wait or how much mass you accumulate, hydrogen burning simply cannot begin in the cloud. This temperature requirement is an absolute limit set by nuclear physics. Achieving 10 million degrees requires compressing the gas. It must be compressed to enormous densities to reach this temperature. Typically, this is around 100 grams per cubic centimeter in the core. For reference, water has a density of only 1 gram per cubic centimeter. So stellar cores are 100 times denser than liquid water. The compression of the gas heats it up through a specific process, the conversion of gravitational potential energy into thermal energy. You cannot get hot enough for fusion without getting dense enough first. Dark stars operate in completely different physical conditions. Their cores might only reach a few 100,000 degrees. This is far below the threshold needed for nuclear fusion. Their densities can be as low as a billionth of a gram per cubic centimeter. This is roughly the density of our Sun's outer atmosphere. These conditions are far too gentle for fusion to ever occur, but they are absolutely perfect for dark matter annihilation to dominate. The key difference between the two is the cooling efficiency. In the early universe, the hydrogen clouds could radiate energy away. They did so through the formation of molecular hydrogen, but this cooling process is very slow and also very inefficient. It is inefficient compared to modern star formation, which is different. Modern star formation benefits from heavy elements that provide cooling channels. Without this efficient cooling, the clouds just heat up as they collapse. They eventually reach a point where the pressure prevents further contraction. This is where the dark matter annihilation changes the game. The heating from the annihilation occurs throughout the cloud's entire volume. It does not just occur at the very center of the cloud. It provides the necessary support against the gravitational collapse. It does so without requiring the gas to reach high densities. The cloud settles into a stable equilibrium state. Dark matter heating balances the radiative cooling of the gas. This equilibrium exists at densities that are far too low for fusion, but they are sufficient for maintaining a stable structure. Calculations have shown that for typical dark matter halo conditions, this equilibrium temperature would be in a specific range, a range of a few thousand to a few 100,000 degrees Celsius. This depends on the dark matter particle's mass and annihilation cross-section. The corresponding density would be low enough that the structure remains puffy. It would remain extended, potentially reaching enormous sizes. This explains why dark stars can grow to become so massive. A fusion star is constrained by the need to maintain hydrostatic equilibrium. It must balance the immense pressures from its nuclear furnace. As fusion stars add more and more mass, they become more unstable. The most massive stars are constantly flirting with catastrophic disruption. There is a clear upper limit to how big a fusion star can grow. It will eventually tear itself apart if it grows too large. Dark stars face no such constraint on their growth. The heating in them is distributed throughout their volume. The entire structure is stable, and adding more mass is simple. It simply means incorporating more volume into the glowing cloud. They can grow to millions of solar masses while remaining structurally sound. The limits on their size come from the dark matter supply. They also come from competition with other formation mechanisms, not from any kind of internal instabilities within the star. These specific conditions existed for only a narrow window of time, a narrow window of cosmic history in the early universe. Once heavy elements began to pollute the gas, things changed. The improved cooling efficiency made fusion star formation much easier, and it made dark star formation much less favorable. The era of the dark stars came to an end, but their remnants might still exist in the universe today. When the James Webb Space Telescope began returning its first deep field images, astronomers experienced a mixture of excitement and utter confusion. The telescope had delivered on its promise to see the early universe. It revealed galaxies from the earliest cosmic epochs with incredible clarity. But the properties of these early galaxies made absolutely no sense. They did not fit into our conventional formation models. They were far too bright, too numerous, and too mature for their age. Standard galaxy evolution theory predicts a gradual buildup of stellar mass. Small proto-galaxies should form first, then merge with each other. They would then gradually assemble into larger structures over time. The efficiency of star formation should be relatively low. It should be low in the early universe because the gas is not yet enriched. It is not enriched with the heavy elements needed for cooling. Without these metals, the cooling is very inefficient, and the process of star formation proceeds very slowly. By this logic, the first billion years of the universe should be different. It should produce relatively faint and irregular structures, not the bright, well-organized galaxies the telescope was detecting. the new observations were telling a completely different story. Galaxies at a redshift of 10 were seen by the telescope. This corresponds to about 450 million years after the Big Bang. They were shining as brightly as galaxies that were billions of years older. Some of them appeared to contain huge stellar populations that were equivalent to billions of solar masses. The mass-to-light ratios of these galaxies were all wrong. Their colors were also completely wrong for their age. The sheer number of these bright early galaxies exceeded predictions. It exceeded them by factors of 10 to 100. Some scientists initially suggested that this meant our model was broken. Our entire cosmological model could be fundamentally wrong. If the standard expansion history and dark matter framework could not explain this, perhaps some of our fundamental assumptions needed revision. The phrase universe breaking entered the scientific discourse. Headlines proclaimed that the telescope had disproven the Big Bang, or that it had falsified the existence of dark matter. The reality of the situation was much more subtle and interesting. The issue was not with cosmology itself, but with our models of galaxy formation within that cosmological framework. The models had assumed that all of the early light came from fusion stars. If a significant fraction of it actually came from dark stars, the entire problem would be completely resolved. Dark stars can achieve enormous luminosities very quickly. They can do so without requiring the slow buildup of stellar populations, the kind of buildup that fusion-powered galaxies need. A single dark star with 1 million solar masses can be very bright. It can have 10 billion solar luminosities of light output. This contributes as much light as an entire small galaxy. If early halos were producing dark stars alongside or instead of normal stars, the observed brightness could be explained without invoking exotic physics. The mass budget would work out, and the timeline would also work out. The spectral properties would also roughly match the observations. This interpretation gained a great deal of support from spectroscopic studies. They showed that many early bright objects had unusual characteristics. The gas motions around them were much faster than expected. The chemical abundances in them were quite peculiar. Some of the objects appeared to have massive black holes at their centers, black holes that were far too early in cosmic history. All of these oddities aligned with a new picture of the early universe, a picture where dark stars formed, evolved, and then collapsed. They would collapse into black holes on very rapid timescales. This would seed the growth of the very first quasars. The little red dots discovered in the early telescope data fit this narrative. They fit this narrative absolutely perfectly in every way. They are very compact and they are extremely luminous. They also show clear evidence for accreting black holes. Their red color comes from a combination of dust, obscuration, and redshift. Their high abundance matches the predictions for dark star formation rates. Their decline around 1.5 billion years after the Big Bang corresponds. It corresponds to when conditions became less favorable for dark star formation. Instead of breaking the universe, the new observations were revealing something. They were revealing a previously hidden chapter of cosmic evolution. Dark stars represented a transient phenomenon in the universe. They were important during the cosmic dawn, but then faded away. They faded as the conditions in the universe began to change. We are seeing their signatures now because we finally built a telescope that is capable of observing the universe at that early epoch. The pristine clouds of hydrogen floating in the darkness were waiting. They were waiting for something to come along and ignite them. Imagine gas that has never been touched by the light of a star. Gas that has never passed through a stellar furnace. Gas that has never been processed by any mechanism at all, except for the primordial nuclear fusion that occurred in the Big Bang. This is the starting material for everything that will come later. Roughly 75% of it is hydrogen by mass, 25% of it is helium, with just traces of lithium. Absolutely nothing else exists in this primordial gas. The hydrogen is in its simplest possible form, a single proton that is being orbited by a single electron. The helium consists of 2 protons, 2 neutrons, and 2 electrons. These atoms are the fundamental building blocks of the universe. They are pristine and completely unmodified by any stellar processes. They are spreading through the expanding universe as a neutral gas. They carry no memory of any previous stellar generation. This is because there have not been any previous stellar generations. This is the very first act in the cosmic drama. These clouds of gas are enormous by any human scale. They often span thousands of light years across in size. They contain masses that are equivalent to millions of suns, but they are also incredibly diffuse with very low densities. Their densities are lower than the best laboratory vacuums we can create. The particles in them are separated by centimeters or even meters. They are drifting through space in near-perfect isolation, except for when they occasionally happen to collide with each other. Gravity is a very patient and persistent force. It pulls gently but relentlessly on every single particle. It draws them toward the regions where mass has already begun to accumulate. The dark matter halos provide the necessary gravitational scaffolding. They are the invisible frameworks that guide the motion of ordinary matter. The gas falls along streams toward the densest points. It forms long filaments and eventually concentrates in the halo cores. As the gas falls inward, it begins to speed up. Gravitational potential energy is converted into kinetic energy. This means that the atoms in the gas are moving much faster. When these fast-moving atoms collide with each other, their kinetic energy can be converted into other forms, primarily into thermal energy and into radiation. This is how all cosmic structures heat up during their formation. The faster an object falls, the harder it hits when it arrives, and the more energy gets released in the process. In some of these clouds, the conditions allow for molecular hydrogen to form. 2 hydrogen atoms can bond together, creating the simplest molecule. This molecule can then radiate energy away from the cloud. It does so through its rotational and vibrational transitions. This provides a cooling mechanism that pure atomic hydrogen lacks. The cooling of the gas allows for further collapse. This increases the density, which accelerates molecular formation. This creates a positive feedback loop in the process. These clouds might eventually compress enough to ignite nuclear fusion. They would then become the first population 3 stars. But in other clouds, the dark matter density is very high. It is high enough that annihilation begins before the cooling can take over. The energy that is released by the annihilating WIMPs heats the gas. It heats the gas from within, preventing the runaway collapse. The cloud reaches an equilibrium where it remains diffuse and extended, but it is hot enough to shine with incredible brightness. A dark star has formed instead of a normal fusion star. The chemical purity of these clouds is essential to this process. Even a tiny amount of heavier elements would drastically alter the cooling. It would potentially prevent the formation of a dark star. It would allow the gas to collapse much more efficiently. The narrow window when this pristine gas coexisted with high dark matter densities, this window could not have lasted forever in the universe. Once the first generation of stars began producing heavy elements and dispersing them through powerful supernova explosions, the entire environment of the universe changed fundamentally. This is why dark stars are a phenomenon of the very early universe. They require conditions that existed only before stellar enrichment began, before the gas was contaminated with these heavy metals. They are a one-time occurrence in the history of the cosmos. They will never be repeated in the same way again. The clouds that formed them were very special indeed. They existed in a brief window of time in the universe, between the end of the cosmic dark age and the beginning of metal production. Those special clouds were responding to invisible forces, forces that were pulling them together in the depths of space. The universe does not stay the same from moment to moment. Every single second, the fabric of space itself expands. It stretches the distances between all of the galaxies. It cools the cosmic background radiation as it does so. This expansion is not objects moving through space. It is the space between them that is growing and carrying everything along. The rate of this expansion determines what structures can form. It determines what can form at any given time in cosmic history. In the very first moments of the universe, the expansion was incredibly rapid. It was so rapid that nothing stable could possibly exist. The universe doubled in size countless times in tiny fractions of a second. This period of rapid expansion is known as cosmic inflation. Then the expansion slowed down to a still rapid but more moderate pace. The matter and energy at this time were far too hot and energetic. They were too energetic to form any stable structures. Particles were constantly appearing and disappearing in the plasma. Nothing permanent could possibly condense out of all this chaos. As the expansion continued and the temperatures dropped, the interaction between the particles began to slow down. Quarks formed protons and neutrons in the primordial soup. Protons and neutrons then formed the first light nuclei. Eventually, electrons joined these nuclei to make neutral atoms. Each of these phase transitions occurred when the universe cooled. It cooled below a critical temperature for that transition. Below that temperature, the structures became stable. Above it, they remained completely impossible to form. The cosmic dark age began when the atoms finally formed. It lasted until the very first luminous objects appeared. During this period, the universe was expanding at a specific rate, a rate that was determined by its total energy density. This density was dominated by dark matter and ordinary matter. There was also some contribution from the radiation field. The expansion rate of the universe set a certain time scale. How quickly did the densities decrease due to the dilution, versus how quickly did the structures grow through gravitational attraction? Structures that collapsed faster than the expansion rate could grow. They could overcome the dilution and continue to grow larger. Structures that collapsed slower just got spread out and disappeared. The critical scale for this depended on the mass of the overdense region. It also depended on the era when it was collapsing. In the first few 100 million years of the universe, only dark matter halos below a certain mass could collapse. They had to collapse quickly enough to become bound structures. Larger potential galaxies had not had enough time to fully condense yet. This is why the first luminous objects formed in small halos. They were the fastest to collapse because they had the highest initial overdensities. These mini-halos became the sites of the cosmic dawn. This is where the gas accumulated and formed the first stars. Only later in cosmic history did the larger structures fully assemble. The evolution of the temperature also played a crucial role. The cosmic background radiation cooled according to the expansion rate. It dropped from thousands of degrees at recombination to a few dozen degrees. This happened by 300 million years after the Big Bang. This cooling affected the temperature of the gas everywhere. It provided a baseline that local heating or cooling mechanisms then modified. In regions where the gas was falling into the halos, the temperatures could rise to thousands or even millions of degrees. This was due to the process of shock heating. In regions where molecular hydrogen was forming efficiently, the temperatures could actually drop below the cosmic average. The interplay between cosmic expansion cooling and gravitational heating, all of these processes created a complex temperature landscape. The dark matter annihilation added another heat source to this mix. Its importance depended critically on the local dark matter density. This density was highest in the cores of the dark matter halos. As the universe expanded and the structures grew, the densities decreased. The annihilation rates, which depend on density squared, dropped rapidly. The era when annihilation could power dark stars was therefore limited. It was limited to the period when dark matter densities remained high. All of these factors combined to create a narrow window of cosmic history when dark stars could form and shine. That window is now closing forever in our universe. But something massive is about to collapse from the weight of these giants. Dark stars cannot possibly shine forever in the universe. Their unique power source is finite and will eventually run out. It is limited by the amount of dark matter that is available. The annihilation process consumes the dark matter particles. It consumes them at a rate that is determined by their density. Every single annihilation event removes 2 particles permanently. Eventually, the supply of these particles runs low. The original dark matter that was trapped inside a dark star when it formed. It might last for approximately 1 million years. This sounds like a very long time, but it is brief on cosmic scales. For comparison, a fusion-powered star like our own Sun will burn for a long time. It will burn for about 10 billion years in total. Dark stars live very fast, and they die very young. They blaze with incredible brilliance for a cosmological instant. Then their unique fuel source simply vanishes away. During its lifetime, a dark star can capture additional dark matter. It can capture it from its surrounding environment in space. Its gravitational pull extends far beyond the visible boundary of the cloud. Dark matter particles that are passing nearby can get deflected. They can be potentially captured into orbits around the star. If they pass close enough to the dense central regions, they can lose energy through interactions and become bound. This process of replenishment could extend the dark star's lifetime. It could potentially allow it to shine for tens of millions of years, but this replenishment cannot continue indefinitely forever. The dark matter halos themselves are very dynamic structures. They evolve through mergers and interactions with other halos. When 2 of these halos happen to collide with each other, their contents get stirred up and then redistributed. A dark star that is sitting peacefully at the center of its halo, it might suddenly find itself displaced to the outskirts. This is where the dark matter density is much lower. Once it is displaced, the replenishment rate drops dramatically. When the dark matter density falls below a critical threshold, the annihilation can no longer generate enough power to support the structure. The heating rate inside the star begins to decrease. The temperature of the gas begins to drop as a result. The pressure inside the star also begins to fall. Without sufficient pressure to counteract the force of gravity, the process of collapse finally resumes once again. What happens next depends on the mass and structure of the star. If the dark star has incorporated enough hydrogen and helium, it might have accumulated millions of solar masses of ordinary matter. This gas has been held up by the dark matter annihilation pressure. It has been prevented from collapsing to the high densities needed for fusion. This support was artificial, maintained only by the continuous injection of energy. When that support finally disappears, nothing remains to prevent the collapse. The entire cloud of gas begins to fall inward under its own gravity. There is no fusion process to create any outward pressure. There is no radiation to push back against the infalling material. The collapse is free and completely unimpeded by any other force. It accelerates rapidly as the entire structure contracts. Within a matter of just a few hours or a few days, the material that was once spread across vast distances collapses. It plunges into a region that is smaller than our own solar system. The density of the material increases by factors of trillions. The fabric of space-time itself begins to curve dramatically. It curves under the immense weight of the concentrated mass. The escape velocity at the surface of the object exceeds the speed of light. An event horizon finally forms around the collapsing object. The dark star has now become a supermassive black hole. But this is not a small stellar mass black hole, the kind that is formed when massive stars explode. This is a black hole that starts its life with a huge mass, a mass of 1 million suns or even more than that. It is already in the supermassive category from its birth. It is born fully grown without needing billions of years to accumulate mass. This simple process solves one of the most perplexing mysteries in cosmology. The James Webb Space Telescope keeps finding cosmic monsters, monsters that should not exist in the early universe, black holes that weigh millions or billions of solar masses. They appear in galaxies that formed less than 1 billion years after the Big Bang. These supermassive black holes are known to power quasars. Quasars are the brightest sustained sources of light in the entire universe. Their existence raises a fundamental question for astrophysicists, a question that has troubled them for many decades. How did these black holes grow so large, so incredibly quickly? The problem is one of both time and their feeding rates. Black holes are known to grow by consuming matter from their surroundings. Gas dust and occasionally entire stars fall into their gravitational wells. They release enormous amounts of energy as they spiral inward. This happens in a structure called an accretion disk. But there is a clear limit to how fast this process can occur. There is a speed limit that is set by the laws of physics itself. That limit is known as the Eddington rate by astronomers. It is named after Arthur Eddington, who derived it nearly a century ago. When matter falls onto a black hole, friction in the disk heats it up. The material is heated to millions of degrees Celsius. This superheated gas then radiates with incredible intensity. It radiates, especially in the ultraviolet and X-ray wavelengths. The outward pressure from this radiation pushes against the infalling material. This creates a resistance to any further accretion of matter. If a black hole tries to consume matter faster than the Eddington rate, the radiation pressure becomes so incredibly strong, it blows away the very incoming material that it is trying to consume. The black hole essentially chokes on its own food. It cannot force feed itself beyond this natural limit. For a black hole of a given mass, you can calculate the maximum accretion rate, and therefore you can calculate the maximum growth rate over time. Start with a stellar mass black hole that is formed from a dying star, perhaps 10 to 100 solar masses in total. Let it accrete at the Eddington limit continuously without any interruption. Then calculate how long it takes to reach 1 million solar masses. The answer to this calculation comes out to be hundreds of millions of years. Often it is even longer when you account for realistic complications. But the James Webb Space Telescope is detecting million solar mass black holes. It is detecting them at a redshift of 10. This is just 450 million years after the Big Bang. Some of them appear to be even earlier than that. A black hole was discovered at a redshift of 13.1. It existed only 430 million years after creation. The timeline for this to happen is impossibly tight. Even if it was feeding at the absolute maximum rate from the moment of its formation, a stellar mass seed simply cannot grow large enough, fast enough. You can try to rescue the conventional picture by invoking special circumstances. Maybe these black holes fed at super Eddington rates through some exotic mechanism. A mechanism that we do not yet fully understand. Maybe they had unusually abundant supplies of gas around them. Supplies that somehow managed to overcome the radiation pressure. Maybe the early universe was different in ways that changed the Eddington limit. Each of these explanations requires some special pleading, and each of them stretches the known laws of physics. Or you can simply start with a much heavier initial seed. If the initial black hole already weighs 1 million solar masses, it does not need to grow very much at all to match the observations. It starts its life in the supermassive category, and it can immediately begin powering a bright quasar. The entire timeline problem simply vanishes with this solution. This is known as the heavy seed scenario in cosmology. It requires a formation mechanism that can produce massive black holes directly. It must do so without going through the process of stellar evolution. Dark stars provide exactly this kind of mechanism. When they collapse, they create black holes with very large masses. The mass is set by the total amount of hydrogen and helium in the dark star. If the dark star reached 1 million solar masses before its fuel ran out, the resulting black hole inherits that mass instantly. No long growth period is needed for it at all. No Eddington limit needs to be overcome in this scenario. The supermassive black hole appears in the universe fully formed. The correlation between dark star predictions and the observed early black holes is striking. Dark stars should form in the first few 100 million years. They should exist for roughly 1 million years, then collapse. We should see bright objects at redshifts of 14 to 10. This should be followed by massive black holes appearing shortly after. The James Webb Space Telescope is seeing exactly this pattern. These ancient monsters are not paradoxes after all. They are the fossils of a forgotten dark star era. Picture a black hole that is surrounded by a disk of swirling gas. The gas spirals inward, orbiting faster and faster. It does so as it approaches the black hole's event horizon. The friction between the adjacent layers of the disk converts energy. The orbital energy is converted into a great deal of heat. The inner regions of the disk can reach temperatures of millions of degrees. They then glow brilliantly in the X-ray part of the spectrum. This accretion disk can easily outshine entire galaxies. It is powered purely by the gravitational potential energy of the matter. The matter is falling into the deep well of the black hole. But the brightness of this process creates a problem. Light is known to carry momentum with it as it travels. When photons are emitted by the hot disk, they can strike gas particles. They transfer their momentum and push the gas outward. This radiation pressure opposes the inward pull of gravity. For a given black hole mass and accretion rate, you can calculate the balance. You can calculate whether gravity wins or if radiation wins. Arthur Eddington worked out the mathematics for this in the early 20th century. He showed that for any spherically symmetric accretion onto a compact object, there exists a critical luminosity that cannot be exceeded. Above this luminosity, the radiation pressure will exceed the gravitational attraction. If you try to accrete matter faster and generate more luminosity, you will simply blow away the infalling material. The limit is a fundamental one that arises from the balance of forces. The balance between the force of gravity and the force of electromagnetism. The Eddington luminosity depends directly on the black hole's mass. More massive black holes have a stronger gravitational pull. They can therefore accrete matter much faster before hitting the limit. But the mass doubling timescale is still measured in tens of millions of years. Even under optimal continuous Eddington rate accretion from a 10 solar mass seed, you would need at least 30 mass doubling times to reach 10 million solar masses. That requires hundreds of millions of years of continuous feeding. Real black holes do not accrete matter continuously like this. The supplies of gas around them can fluctuate over time. Feedback effects can also temporarily shut down the accretion process. Powerful outflows can clear the gas from the surrounding region. Mergers and interactions can disrupt the orderly flow of accretion. When you include all of these realistic complications, the growth timescales for black holes become even longer. Models that start from stellar mass seeds and follow their growth, they consistently fail to produce enough massive black holes early enough. They cannot match the new observations from the telescope. Theorists have explored various ways to exceed the Eddington limit. Perhaps some black holes accrete through non-symmetrical geometries. This would allow radiation to escape along certain directions, while matter continues to flow in from other angles. Perhaps extremely dense streams of gas can penetrate deep into the potential well. They could do so before the radiation pressure becomes effective. Perhaps powerful magnetic fields can channel the material in certain ways that bypass the standard limits on the accretion rate. These mechanisms might work under some very specific circumstances, and they could contribute to faster than Eddington growth for brief periods. But sustaining this super Eddington accretion for millions of years, it requires an extraordinary fine-tuning of the conditions, and even doubled or tripled rates do not solve the timeline problem. They cannot solve it for the earliest and most massive black holes. The heavy seed scenario cuts through all of this complexity. If you start with a 1 million solar mass black hole from a dark star, it does not need to exceed the Eddington limits at all. It can grow at a more leisurely pace, accreting gas at standard rates. It can still easily match all of the observations. The initial mass head start it has is so enormous. Subsequent growth becomes almost irrelevant for explaining the earliest quasars. This is not just about the numbers fitting the observations, it is about having a physically plausible formation pathway, a pathway that does not require multiple improbable conditions. Dark stars forming in early halos and then shining for their brief lifetimes, then collapsing into massive black holes is a natural sequence. It is a sequence that emerges from the basic laws of physics. The evidence keeps accumulating that nature chose this path. It chose this path during the era of the cosmic dawn. In theoretical astrophysics, the term direct collapse refers to a specific process, the formation of a black hole without an intermediate stellar phase. Normal stellar evolution proceeds through a very well-defined sequence. A gas cloud collapses, then nuclear fusion ignites. The star then burns for millions or billions of years. The fusion fuel in the core is eventually exhausted, and only then does the core of the star collapse into a compact remnant. Direct collapse simply skips all of these middle steps. For direct collapse to occur, you need a massive gas cloud, a cloud that can implode catastrophically without ever igniting fusion. This requires suppressing the nuclear reactions that would normally stabilize it, reactions that would convert it into a normal star. In the modern universe, this is a nearly impossible thing to achieve. Gas clouds are known to naturally fragment as they collapse. They break into smaller pieces that then individually reach fusion condition. The presence of heavy elements provides efficient cooling that accelerates this. The end result is always star clusters, not single massive collapsing objects. But the early universe offered a very different set of conditions. With only hydrogen and helium present, the cooling was very inefficient, and the process of fragmentation was therefore suppressed. Massive clouds could remain intact during their initial collapse. However, they would still heat up from the gravitational compression. They would eventually reach temperatures where fusion would ignite. Direct collapse to black holes remained difficult even in this primordial environment. Unless something provided additional support to prevent the compression, dark matter annihilation provides exactly this kind of support. It heats the cloud just enough to maintain the pressure support. It does so at relatively low densities for the gas. The structure remains stable for cosmologically significant timescales. Then, when the annihilation shuts off due to dark matter depletion, the support vanishes and the collapse proceeds unimpeded. This is a direct collapse with a unique twist to it. The cloud does go through a luminous phase as a dark star, but this phase does not involve any nuclear fusion, and it does not fundamentally alter the final collapse dynamics. When the transition finally occurs, the entire structure implodes. The million solar mass structure implodes at essentially free-fall velocity. Within just a few hours, the material crosses the Schwarzschild radius. An event horizon forms, and the black hole is born. The process is as direct as you can get, while still allowing the object to be visible. Simulations of the collapse of dark stars show that the process is remarkably clean. The structure does not fragment or produce multiple smaller black holes. The implosion is coherent with all the material falling inward. The final black hole's mass equals the initial dark star's mass. It equals it to within just a few % of accuracy. Some of the material might be ejected in the form of relativistic jets, but the bulk of the matter becomes part of the new black hole. This scenario predicts specific signatures that observers could potentially detect. There should be a population of transient events in the early universe, events that correspond to dark stars collapsing in real time. Each of these collapse events would produce a characteristic signature, a rapid dimming as the luminous cloud disappears inside the event horizon. This might be accompanied by a burst of gravitational waves. The waves would come as the new black hole rings down to its final state. Current telescopes might not be sensitive enough to catch these events. They would be extremely rare and also extremely distant, but future facilities with wider fields of view could spot them. Finding even a handful of these dark star collapse events would be huge. It would provide smoking gun confirmation of the entire formation pathway. The implications of this extend beyond just explaining the early black holes. If direct collapse through dark stars was a common process, it means the seeds of today's supermassive black holes have a different origin, a fundamentally different origin than anyone had expected. Every giant black hole at the center of every major galaxy. It might trace its lineage back to a dark star that collapsed, a dark star that collapsed some 13 billion years ago. The ancient monsters that are ruling galactic centers today, they were born from invisible matter destroying itself. They were born in the faint light of the cosmic dawn. Black holes do not remain isolated forever in the universe. Gravity will draw them together over cosmic timescales. When two black holes orbit each other very closely, they radiate gravitational waves that carry away orbital energy. The orbit shrinks and the black holes spiral inward. Eventually they will collide and merge into a single larger black hole. This process was confirmed by gravitational wave detectors in recent years. It plays a crucial role in building up supermassive black holes. If dark stars commonly formed in the early universe and then collapsed, these black holes would have become the nuclei of small proto-galaxies. As those proto-galaxies then merged through gravitational interactions, their central black holes would have been brought together. The merger of 2 million solar mass black holes creates a 2 million solar mass 1. Merge that with another million solar mass hole and you get 3 million. The addition of the masses is very straightforward, but these mergers do more than simply add up the masses. They also can kick the resulting black hole in a random direction. This happens through the conservation of momentum, the gravitational wave emission during the final moments of the merger. It is not perfectly symmetric in all directions. The waves carry more momentum in some directions than in others. And conservation laws require the merged black hole to recoil. It recoils in the opposite direction of the momentum imbalance. These kicks can reach velocities of hundreds of kilometers per second. In small proto-galaxies with relatively weak gravitational potential wells, these kicks could be strong enough to eject the black hole entirely. The merged black hole would be flung out of its host galaxy. It would then be left to wander through intergalactic space. This sounds like it would deplete galaxies of their central black holes, but the effect is actually much more subtle than that. The ejected black holes do not simply disappear from the universe. They carry all of their mass with them as they travel, and they remain gravitationally bound to the larger scale structure. Over long periods of time, these wandering black holes can settle back down. They can settle back into deep gravitational potential wells. They often will merge with other wandering black holes, or they will find their way to the centers of larger galaxy assemblages. The net effect of this process is to concentrate the black holes. They are concentrated in the deepest potential wells. These wells correspond to the most massive galaxies. This produces exactly the correlation that we observe in the modern universe. More massive galaxies are known to harbor more massive central black holes. The merger cascade also explains the timing of quasar activity. Quasars are at their brightest when the black holes are actively accreting gas. They are accreting it at very high rates to be so bright. Mergers are known to trigger inflows of gas toward the galactic centers. They do this by disrupting the orderly motions of the gas. The gas was once in stable orbits around the galaxy. The chaotic gravitational environment during a merger funnels the gas. It funnels the gas inward, feeding the central black holes. This process then powers the bright quasar emission that we see. The new telescope observations show that many early galaxies are merging. They appear to be in the process of merging, or have recently merged. Their disturbed morphologies, tidal tails, and multiple nuclei are all visible. They are visible in the high-resolution images from the telescope. All of these signs point to very frequent interactions. This merger-rich environment would have been ideal for building up black holes. It would have been ideal for building them through the cascade process. Starting with heavy seeds from collapsed dark stars dramatically shortens the timescale. The timescale for reaching billion solar mass black holes. Instead of needing hundreds of millions of years of continuous accretion, you would only need a few tens of merger events to do it. Each of these mergers can be completed within a few million years. From the initial orbital decay to the final coalescence, 10 mergers of million solar mass seeds can produce a billion solar mass black hole. It can do so in roughly 100 million years. This is easily fast enough to explain the earliest quasars. The gravitational wave background generated by these mergers should be detectable. It could be detected with what are called pulsar timing arrays. These are experiments that use the galaxy as a gravitational wave detector. They do so by precisely measuring the arrival times of pulses. The pulses come from distant pulsars in our galaxy. Early hints of this background have already been reported by scientists. Though a confirmation of it will require more data, every piece of evidence seems to be pointing toward dark stars that are seeding a merger cascade that built the supermassive monsters. The monsters that are now ruling the galaxies of today. For many decades, the story of the cosmic dawn followed a simple narrative. First came the dark matter halos condensing out of the void. Then the primordial gas fell into these dark matter halos. Then the gas cooled down and it fragmented into smaller clumps. Then those clumps of gas collapsed to a high enough density, a density that was high enough to ignite nuclear fusion. Then the very first stars were finally born into the universe. These were the population 3 stars, the first generation. They were very massive and also very short-lived. They produced the first heavy elements through their nuclear reactions. They then exploded as supernovae at the end of their lives. They enriched their surroundings with these heavy metals. This enrichment then allowed later generations of stars to form more easily. This eventually led to the formation of galaxies and everything that followed. This narrative assumes that the fusion stars were the first luminous objects. Dark stars completely upend this simple assumption. If dark matter annihilation could power luminous objects before fusion was possible, then the first lights in the universe were not stars in the conventional sense. They were dark stars which were hybrids of ordinary matter and exotic particles. They were shining through a fundamentally different energy generation mechanism. The implications of this are truly profound for cosmology. The chemical enrichment history of the universe might need to be revised. If dark stars dominated the early luminosity of the universe, they did not produce any of the heavy elements that we see today. This is because they never underwent the process of nuclear fusion. The metals that enabled the later star formation had to come from a different source. They probably came from true fusion stars that formed slightly later. The sequence of events in the early universe becomes more complex. It also becomes much more interesting as a result. Cosmic reionization is the process by which the universe transitioned. It transitioned from being full of neutral hydrogen to ionized hydrogen. This process might have been driven partially by dark stars. It might have been driven primarily by dark stars, not population 3 stars. Dark stars could have produced a copious amount of ultraviolet radiation. This radiation would be capable of ionizing the surrounding gas. Their large sizes and high luminosities would have made them very effective at carving out large ionized bubbles in the neutral hydrogen fog. The timeline of structure formation might also need to be adjusted. If dark stars formed in smaller, denser halos than fusion stars, they could have appeared much earlier and in different locations. The spatial distribution of the early luminous objects would then reflect this. It would reflect the dark matter halo properties more directly. It would not have the filtering effects of gas cooling and fragmentation. These are the effects that affect normal fusion star formation. Galaxy formation theories are built on the assumption of stellar feedback. Stellar feedback is thought to drive much of the evolutionary process. These theories might be incomplete if dark stars were common. Dark stars do not explode as supernovae at the end of their lives. They do not produce any strong stellar winds during their lifetimes. Their feedback is primarily through the heating and ionization of gas. This is done by their powerful radiation, not through mechanical energy. If dark stars were common, the early galaxy environment was much gentler. It was gentler than the models assuming population 3 supernovae predict. This does not mean that fusion stars were absent or unimportant. Most of the evidence suggests that both dark stars and fusion stars coexisted. They coexisted during the era of the cosmic dawn. They would have formed in different environments or at different times. They could have formed within the very same dark matter halos. The relative importance of each population remains an open question, a question that the new telescope observations are beginning to constrain. But the possibility that dark stars came first and dominated the early luminosity, this forces a rethinking of our basic assumptions. Assumptions about how structure emerged from the primordial darkness. The universe's very first light might have come from invisible matter that was destroying itself in a flash of energy, not from atomic nuclei that were fusing together in a star's core. The dawn of the cosmic dawn was darker than we had ever imagined. Dark matter has been haunting the field of physics for nearly a century. We know that it exists, and we can measure its gravitational effects. We can map out its distribution through gravitational lensing. We can also map it through the dynamics of galaxies. But we have never been able to detect a single dark matter particle directly. It remains the ultimate invisible actor in the cosmic drama. It is shaping the entire universe while refusing to show its face. Every single attempt to directly catch a dark matter particle has failed. Deep underground detectors are shielded from cosmic rays from space. They wait patiently for a WIMP to collide with a xenon nucleus. This would produce a tiny recoil signal that could be detected. Decades of searching with increasingly sensitive instruments have yielded nothing. The parameter space where WIMPs could be hiding continues to shrink. Experiments are setting ever tighter limits on their interaction cross-sections. Particle colliders have also come up completely empty-handed. The Large Hadron Collider was partly built to discover new particles like supersymmetric particles that could be dark matter. After many years of operation and thousands of collisions, no convincing signals of these new particles have emerged. Either the dark matter particles are heavier, or they interact more weakly, or they are not the type of particles that colliders can produce. Indirect detection through their annihilation products has been frustrating. Searches for excess gamma rays from the galactic center have been conducted. They have produced some hints and anomalies, but nothing conclusive. Every promising signal has eventually been explained by something else. More conventional astrophysical processes are usually the culprit. The dark matter signature remains incredibly elusive to us. Dark stars offer a completely different approach to this problem. Instead of trying to detect individual particles in controlled experiments, we can look for the collective effects of enormous numbers of particles that are annihilating in the very early universe. The signal is not just a few scattered photons or a single nuclear recoil. It is entire stars that are shining across cosmic distances. They are powered by the heating from dark matter annihilation. The sheer scale of this phenomenon makes it detectable. It is detectable in ways that individual particle interactions are not. If the dark star interpretation of the new observations is correct, we are finally seeing dark matter annihilation in action. The spectrum, luminosity, and evolution of these objects encode information about the dark matter particles' properties. The annihilation cross-section determines how much power is generated. The particle's mass affects the temperature and size of the dark stars. The nature of the annihilation products influences the detailed spectrum. By studying dark stars as a population of objects, astronomers can constrain the properties of dark matter. They can do so through a kind of stellar archaeology, not through particle physics experiments on the Earth. The constraints might not be as precise as laboratory measurements, but they are independent and complementary to those efforts. They probe the behavior of dark matter under extreme conditions that can never be replicated in terrestrial experiments. Extreme densities in the early universe, when particles were much more likely to interact. Catherine Fries has argued that identifying these supermassive dark stars, it opens up a whole new field of observational astronomy, a field that is focused on dark matter-powered objects. This field would use telescopes and spectroscopy, not particle detectors. It would be used to study the invisible substance that dominates the universe. The techniques are completely different from traditional dark matter searches, but the ultimate goal of both of them is the same: understanding what dark matter is and how it behaves. The cosmic irony of this situation is truly remarkable. The invisible finally becomes visible through its effects on the visible. Dark matter, which refuses to emit or absorb light, it becomes detectable by making clouds of hydrogen shine. The shadow is revealing itself by casting a bright light. Anna Christina Eilers and her team are using the new telescope. They are studying the environment surrounding 5 of the earliest known quasars. These blazing beacons of light exist at very high redshifts. They formed when the universe was between 600 and 700 million years old. Every conventional model had predicted that they should be embedded in very dense regions that are packed with gas and protogalaxies. The observations, however, told a completely different story. Some of the quasars did show exactly the expected environment. They were in rich fields with numerous companion galaxies. They had abundant streams of gas and obvious signs of ongoing mergers. These particular systems made perfect sense according to the standard theories. The black holes in them had plenty of material to feed on, and they could plausibly have grown through continuous accretion. But other quasars appeared to be sitting in cosmic voids. Their surroundings were surprisingly empty of any companion galaxies, and they lacked the dense gas concentrations needed to feed a growing black hole. The term middle of nowhere appeared in the scientific papers. How can a black hole that weighs millions or billions of solar masses exist? How can it exist in a region with such minimal matter density? The paradox only deepens when you consider the energy requirements. Black holes require a continuous feeding to power their quasar luminosity. A bright quasar is converting matter into energy at very high rates. It is equivalent to consuming several solar masses per year. Without a steady supply of gas, the accretion disk would empty quickly, and the quasar would simply shut off and disappear. Isolated quasars should therefore be fading away very rapidly, yet many of them show no evidence of dimming at all. The collapse of dark stars provides a natural explanation for this. If a dark star formed in what was initially a dense dark matter halo, it would shine very brightly during its annihilation-powered phase. But the dark matter halos are not static objects. They move through space and interact with other halos. They also respond to the large-scale gravitational flows. A halo that was very dense when the dark star first formed, it might have been disrupted by powerful tidal forces, disrupted by the forces from nearby structures at a later time. When the dark star collapses into a black hole, the resulting quasar appears in whatever environment the halo is in. It appears in the environment the halo happens to occupy at that moment. If the halo has been stripped of much of its gas through interactions, the quasar would then find itself in an isolated state. It can continue to shine for a while by consuming the remaining gas. The gas that is in its immediate vicinity can fuel it, but it lacks the massive reservoirs of gas needed for sustained luminosity. This scenario predicts that some early quasars should appear isolated. This is exactly what the new observations are showing us. It also predicts that these isolated quasars should be relatively young. They should have been recently formed from a dark star's collapse. They should not have grown through long periods of accretion. As more telescope data becomes available, this prediction can be checked by measuring the ages of the quasars and comparing the isolated ones, comparing them to the ones that are embedded in dense systems. Another possibility involves the mobility of the dark stars themselves. If the dark stars form slightly offset from the halo centers, or if mergers had displaced them from their original positions, they might have collapsed in regions that appear to be empty. They would appear empty when viewed from very large distances. Even though the overall halo structure remains completely intact, the resolution limits of the telescope might not be sufficient. Not sufficient to detect the diffuse gas that is actually present. Both of these explanations involve the existence of dark stars, and both of them differ fundamentally from the conventional quasar formation scenarios. The isolated quasars are not anomalies or failures of our theories. They are the natural outcomes of a dark star formation pathway. Their very existence strengthens rather than weakens the case for dark stars. They strengthen the case for them being the heavy black hole seeds. The emptiness that is surrounding some of these early monsters. It is not a mystery that needs to be explained away. It is a signature of their exotic and unusual origins. Among the 4 dark star candidates that were initially identified, one of them stands out for its extreme distance from us. Spectroscopic measurements have placed it at a redshift of 14. This corresponds to light that has traveled for over 13 billion years. When this light was first emitted, the universe was only 300 million years old. This is roughly just 2% of its current age. Redshift 14 is not the current distance record in astronomy, but it ranks among the most distant confirmed objects with detailed spectroscopy. The light that we receive from this distant object has been stretched. It has been stretched by a factor of 15 through cosmic expansion. Ultraviolet photons that were emitted at the source appear as infrared light. They appear as infrared by the time they reach the telescope's detectors. This extreme stretching means that even very hot, bright objects appear different. They appear to be very red and also very faint. Detecting an object at this incredible distance requires extraordinary sensitivity. The signal from it is incredibly weak after its long journey. Foreground galaxies can block or distort the light from it. Cosmic rays can also mimic these faint point sources in the images. Separating the genuine detections from instrumental artifacts requires care. It requires careful analysis and multiple confirmations. The telescope's spectroscopic capabilities made this detection possible. Rather than relying solely on imaging in multiple filters, the telescope could split the light into its component wavelengths. The resulting spectrum shows absorption and emission features. These features are at specific wavelengths determined by atomic physics. These features are then redshifted by exactly the right amount, an amount that corresponds to the expansion of the universe. The spectrum of this redshift 14 object shows certain characteristics that do not match any known type of galaxy. The emission lines in its spectrum are too weak for its overall luminosity. The continuum shape of its spectrum is also wrong for a stellar population. The absorption feature at 1640 angstroms is present. This is the potential dark star smoking gun, and it appears clearly. It appears clearly despite the object's extreme faintness. Everything about the spectrum of this object suggests something exotic. If this is truly a dark star, it represents the earliest known example. 300 million years after the Big Bang is remarkably soon. It is remarkably soon for any kind of structure to form. Dark matter halos at this early epoch would have been quite small, perhaps only hundreds of thousands of solar masses in total. Yet somehow, a massive dark star managed to form in one of them, and it managed to shine brightly enough to be detected across cosmic distances. The early formation time of this object has implications for dark matter. To produce observable dark stars this quickly requires efficient dark matter concentration in the first halos. The particle physics parameters must fall in a very narrow range. Annihilation must be strong enough to power the dark stars, but it must also be weak enough that not too much dark matter annihilated away. This object also provides the longest look-back time for studying dark stars. If the dark star interpretation is correct, we are seeing the phenomenon. We are seeing it very close to its actual beginning. The pristine conditions at 300 million years represent the optimal environment. The optimal environment for the formation of dark stars. Later times in cosmic history involve more contamination from heavy elements and more disruption from mergers and from stellar feedback. The detection of this object pushed the telescope to its absolute limits. Fainter, more distant dark stars might exist out there, but they remain beyond our current capabilities to detect and characterize. Future instruments with greater collecting area will be needed, or better spectral resolution will be needed to push the frontier further back toward the end of the cosmic dark age. But this single detection at redshift 14 proves something. It proves that the telescope can see back to the cosmic dawn, and it can resolve individual luminous objects from that era. The infancy of our universe is no longer hidden from us. It is no longer hidden behind an impenetrable veil of darkness. When the telescope first revealed massive, bright galaxies at high redshift, some scientists worried that cosmology itself might be wrong. If galaxies were forming too quickly and were too massive and were too mature for their age, then perhaps the Big Bang model needed revision. Perhaps dark matter was not a real phenomenon after all. Perhaps the expansion history of the universe was different from what the cosmic microwave background measurements indicated. Headlines in the media proclaimed that the telescope had broken the universe. This concern was not entirely unreasonable at the time. The standard cosmological model is called lambda CDM. It makes very specific predictions about how structure should form. Dark matter collapses into halos, and then baryonic matter falls into those halos. Stars then form through the process of gas cooling and fragmentation. Galaxies then build up gradually through a process of hierarchical mergers. Each of these steps takes a certain amount of time, and the total timeline from the Big Bang to galaxy formation is constrained. It is constrained by the expansion rate and the growth of structure. If observations showed mature galaxies with billions of solar masses in stars, galaxies at a redshift of 12 or 15, for example, the timeline for this to happen would be impossibly short. There would not have been enough time for the hierarchical assembly, not enough time to produce such massive systems so early. The observations would then contradict the model in a fundamental way, a way that could not be explained by just tweaking the parameters. But the existence of dark stars resolves this apparent contradiction. The bright objects that the telescope detected do not need to be galaxies. They do not need to be full of normal fusion stars. They can be single dark stars or small groups of dark stars, each of them shining as brightly as billions of suns. The mass in stars can be much lower than the total luminosity suggests. This is because the mass-to-light ratio for dark stars is very different. It is different from that of fusion-powered stellar populations. When you reanalyze the observations, assuming a mix of stars, a mix of dark stars and fusion stars, not fusion stars alone, the tension with the cosmological models simply disappears. The required stellar masses drop to levels that are easily produced. They can be produced by the hierarchical assembly process. The formation timescales become consistent with the standard theory. The apparent crisis was just an interpretation problem. It was not a fundamental failure of our cosmological model. This resolution is very elegant because it requires no modification to the underlying laws of physics at all. The lambda CDM model remains completely intact and valid. The expansion history of the universe stays the same. The properties of dark matter do not need to be adjusted. All that changes is our recognition that dark matter can power luminous objects. It can do so under the conditions present in the early universe, something that theorists had predicted years before the telescope launched. The little red dots that appeared impossible to explain as galaxies, they make perfect sense as dark stars or as small galaxies. Galaxies that are hosting massive black holes formed from collapsed dark stars. Their red colors, their compact sizes, and their rapid evolution. Their unusual spectra all emerge naturally from the dark star theory. What had looked like a deep crisis becomes a major discovery. This episode illustrates both the robustness and the limitations of our models. The models correctly predict that bright objects should exist. They should exist in the early universe, but they struggle to identify what type. What type of objects would dominate the early luminosity? Dark stars represent a gap in these models, a phenomenon that should have been included. It should have been included from the very beginning, but it was not widely considered until the observations forced the issue. Going forward, simulations of early galaxy formation will need to be updated. They will need to incorporate the physics of dark stars. Alongside the physics of normal fusion star formation, the relative importance of each mechanism probably varied. It varied with the environment, the halo mass, and the cosmic time. Understanding this complex interplay will require sophisticated new models that can track both dark matter and baryonic matter. They will track them through the entire process of cosmic evolution. The universe is not broken as some had feared. It is just stranger and much more interesting than we had realized. The 4 dark star candidates that have been identified so far, they are likely just the beginning of a new field of study. The James Webb Space Telescope has surveyed only a tiny fraction of the sky, and most of its data has not yet been analyzed for dark stars, not with dark star detection as a primary scientific goal. Catherine Fries and her collaborators are developing new search algorithms, automated algorithms that can scan through thousands of spectra. They are looking for the characteristic signatures of dark stars, signatures that human analysts would take years to find manually. Machine learning offers some very powerful tools for this task. You can train a neural network on simulated dark star spectra, and on the spectra of known galaxies, and then let it classify the real data. The algorithm can process the data far faster than any human, and it might be able to identify subtle patterns that visual inspection would miss. Early tests of these new methods have shown some promising results. Automated searches have recovered the known candidates, and they have flagged additional objects of interest for follow-up. Expanding this search will require more telescope time. Telescope time remains the most precious commodity in astronomy. Every major observatory is completely oversubscribed with proposals. There are far more proposed observations than there are available hours, convincing the time allocation committees to dedicate significant resources to these dark star searches. It requires strong preliminary evidence that the phenomenon is real and that it is scientifically important to study. The initial detections have now provided that necessary evidence. They have opened the door to more extensive follow-up campaigns. Future observations will focus on several important goals. First, they will work on confirming that the candidate objects are truly dark stars. They will do this by obtaining higher resolution spectra that can definitively rule out any alternative explanations. Second, they will try to measure the abundance of dark stars. They will measure it as a function of redshift, to trace their history. Third, they will search for dark star collapse events, or they will search for their immediate aftermaths. This would be to catch the transition from a dark star to a black hole. Fourth, they will look for dark stars in different environments. This will be to understand what conditions favor their formation. Other telescopes will also contribute to this ongoing effort. The Atacama Large Millimeter Array can detect molecular emission. It can detect it from the gas that is surrounding the dark star candidates. This will reveal their immediate physical environment. The Chandra X-ray Observatory can search for X-ray emission from the accretion onto the newly formed black holes. Gravitational wave detectors might eventually catch the signals from the mergers of black holes that are dark star remnants. Ground-based, extremely large telescopes are coming online. They will do so in the next decade and will have huge mirrors. Their collecting areas will be several times larger than the current telescope. They will be able to detect even fainter objects from even earlier times in cosmic history. These facilities will push the dark star search toward redshift 15. They will be approaching the absolute earliest moments, when any luminous structures could have formed. The long-term goal of this research is to construct a complete census of all the dark stars across cosmic history. How many of them formed, and when did they appear and disappear? What were their typical masses and their typical luminosities? How did they influence their surroundings through their radiation and through their eventual collapse into massive black holes? Answering all of these questions will require decades of observations. It will require observations across multiple different wavelengths, and it will require using a variety of different facilities. But the scientific payoff is truly extraordinary. If dark stars are confirmed as a major population in the early universe, they will become a new tool for studying both cosmology and particle physics. Their properties will constrain the dark matter particle's mass and its annihilation cross-section and its distribution. Their abundance will test our models of structure formation. Their collapse provides the heavy seeds for the supermassive black holes, seeds that our conventional theories simply cannot explain. The first dark stars shone some 13 billion years ago, and they vanished after their brief lifetimes of just millions of years. They existed in conditions that will never be repeated. They were powered by processes that we are only now beginning to understand. Now, after traveling across most of the observable universe, their faint, ancient light has finally reached us on Earth. We are now seeing the echoes of the cosmic dawn. We are seeing the reflections of a time when invisible matter made the first light. A time when invisible matter made the first light shine. The universe keeps its secrets for billions of years. But eventually, everything that is hidden comes into view. The dark stars waited patiently in the ancient past. They waited until we built instruments that were capable of seeing them. They were always there, waiting to be discovered. We just needed to look far enough back into the darkness to find where the first light came from.